So we're going to talk a little bit more about how to tell whether two triangles are going to be similar or not. Oops. Identifying similar triangles. We notice that one way we have of doing it is to notice that the first method is to notice that all three angles of one triangle are equal to the three angles of the other. Two, all three sides, all three sides of one triangle have lengths that are a fixed scalar multiple of the other lengths. The lengths in the other triangle. And one last way we can do it is if two angles match, the two angles of the triangles match and the corresponding sides are proportional, then the triangles are similar. So we notice that that first case is pretty straightforward. We notice that if we look at examples, if we looked at one triangle had angles of 45, 55, and let's make it 80. And then the other triangle has angles 55, 45, 80. We notice that those triangles have to be similar triangles. The triangles, let's just call them ABC and DEF. We notice that triangle ABC has to be the same, it has to be similar. Triangle ABC has to be similar to triangle DEF. And so you actually notice that's a fairly common notation. We notice when we write triangle ABC being similar to triangle DEF, we mean in that order. We know that A corresponds to D, we know B corresponds to E, and C corresponds to F. And so we would not want to say, we can't say triangle ABC is similar to triangle EDF, because we notice that A doesn't correspond to E, B doesn't correspond to D. It's not going to work out. So we notice we can also do it. We had discussed if we had one triangle was 6, 7, and 9, we notice that if the other triangle was 24, 28, 36, we can verify that those are going to be similar. So let's make these ABC again. We notice that if we look at 36 divided by 9, that equals 4. If we look at 24 divided by 6, that equals 4. If we look at 28 divided by 7, that equals 4. And so again, that tells us that triangle, notice we could do it in whatever order we like. If we said triangle BCA, we would say that's similar to triangle EFD. And why did I do it that order? The order is completely arbitrary, but we have to make sure that the orders match. So if we go BCA, we have to make sure that corresponds to triangle EFD. Oh, actually, forgot about one more way you can do it. We might wind up noticing that if we had a case where we wanted, if we had angle, if all we know is this angle is 30 degrees, and we know this side is 8 and this side is 12, and we don't know anything about the third side, so let's just call this ABC again. And then the other triangle, we have the same 30-degree angle, and we said make it 24 and 36. We notice that if we have the angles match and the two sides are proportional, that forces the third side to be proportional. So that forces, so a fourth method we can use, method 4, to determine similar triangles. If one angle matches for each triangle, and the pairs of corresponding sides, have the same ratio, then the triangles must be similar. There's something we might learn later on. It's not something you need to know, but it's something interesting if we have time, called the law of cosines, that turns out once we know those two sides, 8, 12, and the angle 30, we actually have a way, it's complicated, but there's a way, we have a way to get the third side line. It's a little bit messy though. That'll happen another week. And again, it's not something you need to know. Just interesting. And so we'll actually often call that first method is often called the angle method. Angle method. For A, and this fourth method is sometimes called angle, side, angle. Sorry, side, angle, side. We'll play with that a little bit more later. And then technically we can call that the second method side, side, side. Method 3 is technically method 1, just because if two angles match, the third angle has to match as well. And so it's pretty much the same thing as angle, angle, angle. So one more thing to mention is that the sum of angles for any triangle is always 180 degrees. And so we notice that if we had a triangle that was 30, 40, and x, we actually know what x is. We know the 30 degrees plus 40 degrees plus x has to equal 180. And so we know 70 degrees plus x has to equal 180. We can subtract 70 from both sides. And we know that x equals 110 degrees. And we also notice that because of that, this triangle is not drawn to scale. You'll notice that many triangles many figures in geometry, you'll have a statement that the figure is not drawn to scale. So technically, we should have drawn it something more like this. Something like 30, 40, 110 is closer to reality. Still not perfect, we'll need a protractor to figure that out, but it's a little bit closer to what the actual triangle would look like with it. Angle measures 30, 40, and 110.